All right, so yesterday we sort of wrapped up the topic of ionic bonding, starting with ionic structure and then the properties of ionic compounds. So they form, giant ionic lattices. Uh, in case of sodium chloride, each atom of chlorine is attracting 6 atoms of sodium, and vice versa. Sodium is attracting 6 atoms of chlorine. They are larger structures as well, and because of those giant ionic lattice structures, there are solids at room temperature with high melting and boiling points. They are hard substances. They dissolve in water because water is a polar solvent, and I discussed why that is, because it has slight charges on the oxygen and hydrogen atoms within the molecule, and that helps split the ions apart for ionic substances. They conduct electricity when molten or aqueous, right? And that is because electricity is a flow of charge. And so the ions are free to move about when they are either in the molten state or in aqueous state, so they can flow. When we talked about the formula for ionic compounds, right? I had left this yesterday because it was a concept I had covered earlier, but it's been requested to go over this again, so I will today. Oxidation number. Oxidation number is basically in ionic bonding how many electrons have been gained or lost.
Ade, sorry for screen sharing. We cannot see you.
Oh my! Could have pointed that out as soon as I started speaking. Keep forgetting that. It is embarrassing. There you go.
Yeah.
You can see that.
Yes.
Anindu.
Yes, sir. Yeah, I
Okay.
clear.
That's your name, Anindu, right?
Yeah.
Yeah. Okay. All right. Apologies for that. All right. So electrons are gained and lost in ionic bonding, and so when electrons are gained, right, that is right, the oxidation number decreases, and so that is called reduction. When electrons are lost, right, the oxidation number increases, and that is called oxidation, right? And we went over an example of oxidation reduction, or together they are called redox. So we had iron 2 sulfate, which is a pale green compound, and we added potassium magnate 7, which is like the Roman numerals here represent the oxidation number, right? So this is 7, right? So it has lost 7 electrons. This guy is 2, so it has lost 2 electrons, right? And when you add these two together, you can observe changes in the oxidation number because these are transition metals and they usually form colored compounds, right? So iron 2 sulfate is pale green, and what you notice when you add potassium manganate 7 to it is that it changes color to pale yellow, which means it has gone from iron 2 sulfate to iron 3 sulfate. That means iron has lost an electron further and is now in the +3 oxidation state. That means it has been oxidized. Now, what's happening to the potassium magnate 7? Well, its color has changed from pale purple to very pale pink, and that tells us that it's gone from the +7 oxidation state to the +2 oxidation state. So it's gained 5 electrons, and that means it has been reduced because the oxidation number has decreased. Okay. And
Yeah.
lastly, right, an oxidizing agent. So what is an oxidizing agent? An oxidizing agent is one that oxidizes another substance and is itself reduced. A reducing agent reduces another substance and is itself oxidized. Okay.
Yeah.
Now, right, before talking about the formula
Sir,
for
the line is not clear.
the line is not clear, meaning you mean the definition of oxidizing agent and reducing agent, or the written you can't make out what's written? Okay. So I'll just explain that again. Right? Because oxidation means losing electrons, or the oxidation number,
I think the signal issue.
increases. Right? So when chemicals react, right, what tends to happen is one becomes oxidized, the other becomes reduced. Right? So in this case, we know that the iron 2 sulfate, the iron in the compound, was oxidized. What was it oxidized by? It was oxidized by the potassium magnate 7. Right? And therefore, potassium magnate 7 is an oxidizing agent. Means it helped in the reaction oxidize the iron, and itself was reduced. So it went from 7 to 2, it gained electrons, but it helped iron lose electrons. Okay? And similarly, reducing it, right? So it reduces another substance. So the oxidation number for another substance is decreased. So what's happening to magnet 7? It's going from 7 to 2. So it's being reduced. What caused this reduction? Iron to sulfate. Okay? So itself is oxidized. The iron to sulfate is oxidized. It caused the reduction of the magnet 7 to the manganese 2.
Sorry to interrupt, sir. The new student left.
That's unfortunate. Right. Now, this is one example. Right. Another example that's given in the textbook for IGCSE and O level as well, right, is of, right, potassium iodide. So what's happening with potassium iodide? Right, potassium iodide is it's a common reducing agent. Right, and just like with potassium manganate and iron, when redox occurs, you have an observable color change. So what's going on? Right? What happens is that you add potassium iodide to a solution of iron 3. So potassium iodide is also Ki, right? The chemical symbol. Right? K is for potassium, I is for iodine. That's potassium iodide. And so you add potassium iodide to an iron 3 solution. And what happens is, right, potassium iodide is colorless. Potassium, right, it's a reducing agent. So what happens is, right, over here, iodine is in the -1 oxidation state. Right, it has gained an electron from potassium. What happens is that when it's mixed in with iron 3, it goes from I minus the ion to I2, which is the diatomic molecule form or the elemental form of iodine, right?
Yes.
And the oxidation number for this is 0. Okay?
Okay.
And so the potassium iodide is colorless, and when it's added to iron 3 solution, it goes from the ion to the elemental form, and the elemental form has, right, a pale yellow color, right, right, a yellow brown in fact. So when, right, your chemicals go from colorless, in this case, in this particular reaction, from colorless to yellow brown, that will tell you that you have formed elemental iodine, right, and that the iodine has become oxidized. It is oxidized because going from -1 to 0, that means the oxidation number has increased. It's oxidized. What happens to the iron 3? Well, if the iodine is becoming oxidized, you could figure out, well, the iron 3 is becoming reduced. And the iron 3 goes to being iron 2. So the oxidation number for iron has decreased. And so it has been reduced. And again, to, right, emphasize what a reducing agent is, the iodine ended up reducing the iron from an oxidation number of 3 to an oxidation number of 2. The iodine or the potassium iodide is a reducing agent, and the iodine itself was oxidized in the process. Okay?
Okay.
That clear?
Yes.
All right. Now, the third reaction, right, is one where the color change is not as significant. And so what we do is we look at the oxidation numbers on the two sides of the chemical equation. And this is a reaction between right, dilute sulfuric acid and magnesium. So you've got magnesium and dilute sulfuric acid. Right, and what you're getting from that is magnesium sulfate, so you're getting a salt. And you're getting hydrogen gas. How does that work? Well, if we write it out, you've got magnesium, and this is in its elemental form, so the oxidation number for magnesium is 0. And then you've got the hydrogen, the sulfuric acid, sorry. So H2SO4, that is the formula for sulfuric acid. And what we're interested in is the hydrogen, right? We know hydrogen, right, in this case is as H plus, right, which means it is oxidized. So, right, what's the oxidation state of hydrogen over here? +1. Now, don't get confused. Oh, there are 2 atoms of hydrogen. Yes, each one individually has an oxidation number of +1. And then what happens over here? So we take the reaction. What is magnesium sulfate? MgSO4. What's happened to the oxidation number of magnesium now? It's become +2. So the magnesium has become oxidized, right? The oxidation number has increased. It's increased. It went from 0 to +2. So the magnesium has been oxidized, right? The sulfate ion, the SO4, nothing's happening to that. Okay, so that is not of our concern. And what happened to the hydrogen? Well, it became hydrogen gas. And just like with elemental iodine, what is the oxidation number of elemental hydrogen, diatomic hydrogen? 0. Right? So it went from +1 to 0. That means the oxidation number was reduced. And so, right, it decreased, sorry, the oxidation number was decreased. And so hydrogen ended up being reduced. Okay?
Yes, sir.
Any questions?
No.
Anindu, any questions? I can understand, right? You're just jumping in for a demo. And
No.
yeah, this might seem like confusing or all over the place, right? But still, if there are any questions, feel free to ask.
Okay.
Okay, so that was about oxidation numbers and redox reactions, reducing agents and oxidizing agents. The thing we left out was formulae for ionic compounds, and it's pretty straightforward and simple. And this involves, again, right, what the oxidation number of the ions that are involved in the ionic reactions is. So we saw sodium chloride. We know that sodium loses one electron, right? And chlorine gains one electron. So similar to the crossing over method that I did earlier, right? We can see, oh, well, only one atom of sodium will combine with one atom of chlorine. And so that gives you the formula for the ionic compound. Now, right, if you have, for example, magnesium chloride, and we know magnesium has an oxidation number of +2, it's in group 2, it's a metal, it loses 2 electrons. Chlorine is in group 7, it gains 1 electron. And so those are the oxidation numbers of each of the ions that would form magnesium chloride. And so magnesium is giving up 2 electrons, chlorine can only take 1 electron. And so what you would need is 2 atoms of chlorine. Each one of those would accept 1 electron from magnesium. And so you would end up with the ionic formula MgCl2. Does that make sense?
Yes, sir.
Then for transition metals, for example, you've got copper, right? Copper can have 2 oxidation states. So you can have copper 1 or copper 2. And both of these can combine with chlorine. Now, in case of copper 1, what you will get is CuCl, because copper is losing 1 electron, chlorine is gaining 1 electron, and so copper chloride, simple. In this case, what you would get, copper in this case is losing 2 electrons. Each chlorine atom or it can gain only 1 electron, so we need 2 of the chlorines to accept 1 electron each from the copper. And so in that case, CuCl2. So this is actually right, how you write it out. It is copper and then the oxidation state in brackets with Roman numerals, chloride, and copper, again the oxidation state of copper in Roman numerals after the name, and then chloride. So copper 1 and copper 2 chloride. Similarly, you've got iron. Right, so iron can be in the +2 oxidation state or in the +3 oxidation state, as we just saw. And this also can combine with chlorine. Iron is giving up 2 electrons, chlorine can accept only 1, so you need 2 atoms of chlorine, and so you get FeCl2. In this case, it's giving up 3 electrons. Chlorine can accept only 1, and so you need 3 of chlorine to accept 1 electron each. And so the formula you get is FeCl3. And what is this called? This is called iron 2. Again, the Roman numerals in bracket for the oxidation number, chloride. Iron 2 chloride. Right? And in this case, it is iron 3 chloride. 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 Sorry about that. Okay. So that's all there is to understand about formula for ionic compounds. Now I will take you to the book briefly. Let me just put that on screen. And what you'll be able to see in the book is a table. Shared it here. Did I share the whiteboard again? I'm rather clumsy today. All right, there you go. And so what you can see is they've given you a table, right, of oxidation numbers or valencies of metals. So all of these guys have a +1 oxidation state. All of these have a +2 oxidation state. And aluminum and iron 3 have a +3 oxidation state. Those are for metals. Non-metals, right, all of these have a -1. These guys have -2, and you don't really have any -3s over here. And then you have what are groups of atoms, right? So they mentioned that. I didn't mention that right now. So I will mention it here. What are molecular ions? So you've got, right, a group of atoms that still act as ions. So you've got, for example, the hydroxide, which is OH, and has a -1 charge. Right, then you've got nitrate, so NO3, so that's 1 nitrogen and 3 oxygens, and it still has an extra electron on it. Right, the manganate 7 that we saw earlier, so that's MnO4 in a bit probably. Okay, so that's MnO4, and it still has a negative charge on it. Right, the sulfate that we just saw with the magnesium sulfate, that is SO4, right? So it's not a single atom, right? It's a molecule, but it has a -2 charge, right? Similarly for dichromate, something we've heard of earlier, and then phosphate, which has a -3 charge. So you've got molecular ions as well. Any questions?
No, sir.
Okay, let me just go back to the whiteboard. Right, so potassium iodide explained over here. Right, magnesium and dilute sulfuric acid explained over here. Just mentioning that again because I think I had the wrong screen on in the recording probably, and so even though my audio was being recorded, perhaps while the book was being displayed, like I said, I'm being rather clumsy today. And then the whole explanation for the formula for ionic compounds. Now that covers the topic of ionic bonding in this chapter, and so now we will move on covalent bonding. And Anindu, right, because we're starting a new topic, perhaps you will find it's easier to follow along now. Covalent bonding. Right, so the whole purpose of bonding, or the aim of bonding for atoms right, is to become stable. And they become stable by having a complete outer shell of electrons, having a complete electron shell, right? As far as we are concerned, that means 8 electrons, 8 valence electrons. Right, so we know, for example, group 1 elements, sodium and the potassium, only have, right, one outermost electron. And so you've got aluminum that has 3 electrons in the outermost shell, and right, you've got carbon with 4 electrons. And so none of these guys have a complete outer shell, right? None of them have 8 electrons. Even the chlorine and everything that we were talking about, the chlorine and the iodine, right, they have 7 electrons. And so they're still not full. Oxygen has 6. Right, the only guys in the periodic table that have a full shell from the get-go are the noble gases. Right, so the uh, helium, right, and krypton and neon and all of these guys, right? So group A. Now covalent bonding ionic bonding involved the transfer of electrons. Covalent bonding involves the sharing of electrons. Between the atoms that are reacting, and it occurs between non-metals, so it takes place, right, with non-metals. So you will not find a covalent molecule with metals in it. So how does this work? Well, let's take a simple example. Just a minute. Right. By the way, right, involves sharing a pair of electrons. Let me write down. So a simple example is the diatomic gases that we have, right? And the simplest example we can have is the hydrogen molecule. We know the hydrogen molecule is diatomic, which means what? H2. Two atoms of hydrogen together to form a hydrogen molecule. But how? So we know, right, if I just draw that out, you've got the nucleus of the hydrogen with 1 proton, and then you have, right, around the nucleus just 1 electron. And hydrogen is the case where you need only 2 electrons to fill up the shell, right, because it is in line with helium. Right, so helium is the one that has 2 electrons. It's the first electron shell, and the first electron shell can only accommodate 2 electrons at most. So what happens is you've got 2 of these guys, you've got another hydrogen atom over here, right, with 1 electron, and they share. And what do they look like when they're sharing? They look like this. The yellows are the nucleus, not drawn to scale or accuracy. And what we have within this overlapping region, right, you draw, or if you want, it to be clear, what you can do is, instead of using two crosses, you can use a dot, just like the dot in cross. And so you've got two electrons. Now, one electron belongs to one of the hydrogen atoms itself, and the other it's sharing with the second hydrogen atom. Similarly, for this guy, right, it has one of its own, and it's sharing the other. And so this way, right, they both now have two electrons, and that means they have a full outer shell. Does that make sense?
Yes, sir.
Any questions?
No.
Okay. Right, so the hydrogen atom is, right, the simplest example you can get. And the way it's written, right, in letters is, right, the diatomic hydrogen is written like this. There, this dash type thing represents the covalent bond. Right, and to be specific, because we'll come across, right, double and triple bonds later, this is a single covalent bond. Right, another example is chlorine. So we know chlorine also exists as a diatomic molecule, but the situation is different, right? So it's Cl2. How is the situation different? We've got the nucleus of chlorine, right? So I'll draw two of these guys because we need two of them. And just drawing the outermost shell. And chlorine has 7 electrons each. So dots for this guy, that's visible enough. And again, they will share because each of them require 1 electron. They've got 7, they need 8 in the outermost shell. And so they will share that 1 lone electron, okay, each, just like hydrogen did. And so what you get is diatomic chlorine. And putting in the electrons, so a cross and a dot. And all the others that were already there, right? And as you can see now, that each chlorine atom has 8 electrons, 7 of its own and 1 being shared with the other atom, right? So you have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And now you have a single bond, right, between the single covalent bond between the two chlorine atoms. That's Cl2. Is that clear?
Yes, sir.
Now, it's not just diatomic molecules that have covalent bonds, right? So, as we said, this is happening between non-metals. And so, uh, right, an example, right, another simple example is HCl, or hydrogen chloride. Now, this is easy to understand because we just talked about hydrogen, we just talked about chlorine, so we know what the situation is. All right, I'm going to stop drawing the nucleus. This is hydrogen. This guy is chlorine. Right? Hydrogen, chlorine, and they come together, and the chlorine atom is obviously bigger. That's around the circle bigger. And what you get when they bond covalently, black, and you've got a sharing of electrons, and that gives you HCl. Right, now when you draw it, you need to be neater with your circles and not as neat. And so hydrogen has 2, which it needed to be stable and complete. Chlorine has 8, and you have HCl. Right, normally you should write it like this, but if you want to show the bond, HCl, that's the covalent bond. And let's then step further and do something that is perhaps not as simple, although if you've understood the concept, then it's all good, right? You just apply it further depending on the scenario you have. So now let's look at methane. Have you ever heard of methane?
Yes.
Right, methane is an organic molecule. It's an organic compound. Right, it has 1 carbon, and the formula is CH4. Right, we know carbon has 4 outer electrons and hydrogen has only 1. So here's carbon, and here are its 4 electrons. And you need 4 of hydrogen. So 1, 2, 3, and 4. Right, and you're adding, you're reacting them, so to speak. Each one of these guys has 1 electron. And what do you get? You get something that looks like this. Big. And you have a sharing of carbon sharing all of its electrons. It's carbon, each hydrogen, and you can see what you need to see is, are they all satisfied? Do they all have a full shell? Hydrogen needs 2. Does it have 2? Yes, each of the hydrogen atoms has 2 electrons. It's happy. Carbon had 4. Now it has 8. 4 of its own, and sharing 1 from each of the 4 hydrogen atoms. So now it has 8. And so it is satisfied. Okay. How do you write this? Well, CH4, because the 4 single bonds, right? Each of these is a single bond. It's the way you write it out. That's how you write it. And this is something you will come across plenty when we reach the chapter organic chemistry, right? Right, so because methane is an organic compound, it's an organic, right? And so we'll talk about it and many others when we get there, right? But this is the 4 covalent bonds, single each. Then the book. Just Google Meet, 15 minutes left, plenty of time. Any questions so far?
Nope.
Okay, then the book gives another example of ammonia, right, which is NH3, so you can go over it yourself. It's pretty much the same thing. And then it gives the example of water, which is H2O. Again, the same thing, right? Two single bonds between each of the oxygen and hydrogen. What I want to go into now is, right, double covalent bonds and triple covalent bonds. Right, covering that in the time we have will help us make good progress. So, right, double covalent bond. An example of that is carbon dioxide, something we are all very familiar with, right? CO2. So what's going on over there? We've got carbon. It has 4 electrons. Again, this is just the outermost shell. And then you've got oxygen, and you've got 2 of them. And each oxygen atom has 6 outermost electrons. And so each oxygen atom needs 2 electrons to become an outer shell, full outer shell, and carbon needs 4 in total. So what's the molecule going to look like? All right, so this is oxygen, this is carbon, oxygen, and what you're having over here is a sharing of 2 pairs of electrons each. So carbon had 4, 2 of its electrons are being shared with the one oxygen, and 2 of its electrons, the other 2 are being shared with the other oxygen, the second oxygen atom. And if you just take a look at this oxygen, oh, by the way, right? So these guys, right? And now carbon has 8 in sharing, oxygen has 8 in sharing, each oxygen atom, and right, so they're happy, it's stable. And the way you write this is you draw 2 lines. Alright, so as I said, that line represents a covalent bond. If it's 2 of them, that means it's a double covalent bond. Does that make sense?
Yes, sir.
Anandu? Any questions? Okay, I guess not. Which I will take as something very positive. Okay, and then finally, right, so for a double covalent bond, they've also given the example of O2, right, which is again a diatomic molecule, right, elemental oxygen, and that's basically 2 oxygens, right, coming together. You have, right, and so that's what's happening, right? There are 6 initially, right? So the 2 that were unpaired are being shared with each, and now so each has 8. And I want to push this today, triple covalent. And the example for that is nitrogen, which is also a diatomic molecule, N2. Okay, and so what's happening in nitrogen? Well, right, how many outer electrons does nitrogen have? It has 5. Right? So if I draw nitrogen, 2 of them, so it has 1, 2, 3, 4, and 5 each. And so you can probably see what's going to happen. Right, what we end up with, you've got 3 of these electrons that are unpaired in each, and those will be shared. I'm just drawing this large so that I can properly show the 3 electron pairs being shared. So dot cross, dot cross, dot cross. Barely managing to squeeze that in. Then you've got right, so you can see that 6 electrons in total are being shared, 3 from each. You have 6 over there, and then 2. Right, so each atom is now has 8 electrons, and it has a full shell. And the way you write that, showing the bonds, right, and so that is a triple covalent. And then finally, they give the example of methanol, right, which is, I think, bringing together, it's a lot of single bonds. So I just fit that in over here to wrap this up finally. And that just shows you, right, that CH3OH, and so that just shows you that covalent molecules can be complex as well. Right, so you've got a carbon, you've got 3 hydrogens, you've got an oxygen and another hydrogen. Right, so that's carbon, that's hydrogen, oxygen, and that's another hydrogen. Right, and all the electrons going in, so dot cross, dot cross, dot cross, and right, oxygen's on. And so you can see, right, the way this looks, we draw it out with the bonds. That's what methanol looks like. Okay?
Yes, sir.
Anandu, any questions? I hope you were able to follow along relatively better than.
No, sir, no questions.
Okay. Right, so that covers the explanation of what covalent bonding is like. Next class, we'll talk about, right, covalent structures and the properties of covalent molecules, and then talk about carbon in specific, because carbon can form a variety of structures depending on how it is bonding with other carbon atoms. And then we move on to metallic bonding, which is a very short section, and then we'll be done with the chapter of bonding. All right, so hopefully next week we'll be done with this chapter, and then we will make our way forward to chapter 4.
Okay.
All right, so I'll see you guys next class. Do remember to, I'll upload the recording, so that will be available, right, for you to review it in case you need it. And right, you have your notes, and do refer to the text. Read the textbook to stay up to date with the classes so that you don't have work piling on. And then also, right, you can obviously ask questions in the next class if anything is unclear.
Okay.
All right, so thank you, and I'll see you next class, inshallah.
Inshallah. Okay.
Okay, sir. Thank you.
Okay, thank you.